All right, let's just jump right into this explainer. Today, we're mapping out what is arguably the deepest structural tension in all of modern physics, the true nature of time's arrow. Think of us as cartographers today, taking a journey through the absolute fundamental fabric of quantum mechanics to figure out why reality actually behaves the way it does. It's kind of the ultimate question, isn't it? Why does time only flow forward? I mean, really think about it. Why does that cup of coffee inevitably cool down on your desk? Why do ripples only ever spread outward when you toss a stone in a pond? This everyday irreversibility is literally everywhere, and yet it happens despite the fact that the foundational, perfectly symmetrical math of the universe tells us time could just as easily run backward. Wild, right? So we're faced with a pretty massive paradox. Down on the microscopic level, following standard Hamiltonian dynamics, the math is completely time reversible. You could theoretically play a film of two atoms colliding entirely in reverse, and literally no physicist would bat an eye. But zoom out to our macroscopic reality, the world you and I live in, and we experience a strict one-way street. Entropy goes up, records accumulate, things decay. So how exactly do we bridge this crazy gap? To navigate this fascinating informational ocean, we need a map. So we'll start with the paradox of time, establish the rules of the realm, and uncover the geometric arrow. From there, we'll learn to sail the orthogonal currents, brave the waters of memory and strong coupling, and finally arrive at the one necessity. All right, part one. The paradox of time. Is it just a statistical accident? Well, for decades, science kind of treated the one-way flow of time as just a statistical likelihood. It was like a rule simply bolted on top of physics. Basically, the thinking was that a shattered glass doesn't magically reassemble itself just because it's overwhelmingly mathematically improbable. It was viewed as an external rule. But here's where we need to totally reframe things. The arrow of time is not a statistical accident. It's not just some probability of large numbers. It is a strict, unavoidable geometric necessity, totally dictated by the intrinsic shape and curvature of quantum state space itself. That's a huge shift. Moving to part two, rules of the realm. Let's look at the minimal axioms. To truly grasp how geometry literally dictates time, we've got to build the fundamental rules of reality from the ground up, without even assuming thermodynamics exists yet. Now, if we accept these 5 basic quantum rules, irreversibility just emerges completely on its own. We start with a continuous state space. We ensure physical processes follow legal quantum rules, what we call CPTP evolution. We recognize open subsystems interacting with an environment. Crucially, we assume absolutely no inherent arrow of time from the get-go. And finally, number 5, we define information purely as the distinguishability between states. The key takeaway, we don't bake time's arrow in, it pops out naturally. Now that 5th rule relies on a really neat concept called Umegaki relative entropy. Think of this as the potential, or basically the height of a hill that a quantum system is rolling down. It essentially measures the informational distance between where a system is right now and its ultimate stationary equilibrium state. Because of those quantum rules we just established, this distance must structurally contract over time. There's no way around it. The universe basically has this undeniable compulsion to erase distinguishability. Honestly, it acts just like a giant leaky sieve for information. Which brings us to part 3, the geometric arrow. Let's unify the flow. This right here is our aha moment of the explainer. The arrow of time isn't some external, invisible clock ticking away in the background. It is an intrinsic, built-in feature of how quantum states are actually shaped. Dissipation, the act of a system relaxing and forgetting information, is physically identical to the system taking the absolute steepest descent down that informational hill we were just talking about. It's all connected. But okay, to know what steepest descent even means, you kind of need to know the shape of the hill, right? Well, that shape is defined by the BKM metric, or Bogoliubov-Kubo-Mori metric. And this isn't just some arbitrary math equation someone picked out of a hat. It is uniquely tied to that relative entropy. It literally defines the specific curvature of our quantum sea. It proves mathematically that what you and I experience as thermal relaxation, again, like your morning coffee cooling off, is simply the steepest, fastest descent downhill that the geometry of the universe actually permits. And honestly, this totally changes how we view history itself. On the left side here, we usually like to think of the past as a hidden archive, right? Like this perfectly intact state just waiting to be recovered if we somehow had enough information. But the right side shows us the operational reality. The past persists only as a geometric constraint on the present. Take the cosmic microwave background radiation, for example. It's a thermal relic. The early universe isn't a microscopic record we can just rewind and watch like a movie. Its phase information and microscopic details have been irreversibly, permanently erased. The past simply limits what the present can actually be. All right, on to part 4, sailing the orthogonal currents. How do we fight the tide? So you might be wondering, if everything is always rolling downhill all the time, how does anything complex even exist in the universe? Well, when a system isn't just passively relaxing, its total dynamics, what we call the Lindbladian generator, splits into 2 parts. Over on the left, you have the gradient flow. This is the downward pull, the geometric decay. Think of it as the river's unstoppable current. But on the right, we have the orthogonal current. Now this is entropy neutral. It acts exactly like a ship's engine, providing thrust perpendicular to the tide, which actually allows the system to sail across the current instead of just being helplessly swept to the bottom. A super cool example of this in action is a 3-level quantum maser heat engine. This is a highly complex system that constantly cycles and actively does work. It deliberately breaks that perfect, pristine thermal relaxation, which physicists call detailed balance. By continuously pumping work in, the maser basically anchors itself to a completely new driven steady state that is super far away from simple thermal equilibrium. The universe's geometry is still ruthlessly trying to pull it down, but that orthogonal current is putting in the work to keep the engine cruising right along the contour lines of the hill. Next up, part 5, memory and strong coupling. Let's talk about memory and shadows. So what happens when we steer our ship into the really chaotic realms? Places where a system is so tangled up with its environment that information actually seems to flow backward. Let's look at the top row. When we look at the entire global system, that is, the system plus its environment, the dynamics are perfectly Markovian. That means they're memoryless. It perfectly follows that steepest descent right down the hill. But check out the bottom row. This shows what happens when we only look at a reduced system, basically ignoring the environment. Suddenly, it looks non-Markovian. We start seeing memory. The geometry appears totally obstructed. But here's the secret. When information seems to flow backward, it's a total illusion. It's just a local shadow. The global universe, the whole shebang, is still relentlessly flowing downhill. So these wild sea monsters on our map, things like memory and strong coupling, they aren't actually resurrecting the past. Through what we call the gradient projection obstruction, we learn that when we ignore the environment, our geometric projection just gets really messy. Strong coupling doesn't preserve history. It just disperses and delocalizes it out into the environment. What we perceive as memory or an information backflow is literally just unerased, hidden distinguishability that's momentarily circulating back into our view. It's definitely not time reversing. It's just the environment briefly showing us what it hasn't quite gotten around to fully erasing it. It's definitely not time reversing. It's just the environment briefly showing us what it hasn't quite gotten around to fully erasing yet. Which brings us to our final stop, part 6, the one necessity. We're looking at the cosmological scale. Let's bring all our navigational charts together here, because this is honestly perhaps the most powerful takeaway of this entire explainer. Are you ready? You do not need to know the beginning of the universe or the exact initial conditions of the Big Bang to know the direction of time. Temporal orientation is entirely local and it is instantaneous. The geometric necessity of the quantum state space sitting right in front of you is perfectly enough to explain why your cup of coffee is cooling down right this very second. To really summarize this profound structural truth, a physical state that differs from its stationary configuration carries within that difference the geometric necessity of its own deformation. Simply put, an out-of-equilibrium state isn't just statistically likely to change, it is geometrically obliged to contract its distinguishability. The arrow of time is absolutely not something dynamics create, rather it's a strict constraint that dynamics are forced to respect. Which leaves us with this final, incredibly provocative question. If the arrow of time is an unavoidable downhill geometric constraint, and if staying alive or running any complex quantum machine requires orthogonal work to sail across that tide, can we exhaustively quantify the true thermodynamic cost of fighting the universe's geometric compulsion to forget, purely by measuring those orthogonal flows? Think about that for a minute the next time you pour yourself a hot cup of coffee. Thanks so much for joining me on this journey today, and keep asking the deep questions.